Hello everyone. Now we will discuss the theory of shear force and bending moment diagram. Bending moment deformation of a straight member. Now in this figure you will see a beam and on which we apply the force, a moment, and you observe the bottom line is longer, the top line is shorter, and middle line retain the same but rotate neutral axis. When any beam bends, you will see the uppermost fiber will contract and the lower bottommost fiber will tense. And there is a one layer of surface which has no effect of neither tension nor the compression. That surface is called the neutral surface. To understand the concept of shear force and moment at any section along the beam, it is best to calculate the values at arbitrarily sections along the beam. We will look at a simple example. Let this is a simply supported beam of a 20 feet beam with a load of 10,000 pound acting downward at the center of the beam. Due to symmetry, the two support forces will be equal with a value of 5,000 pound each. This is the static equilibrium condition for the whole beam. We will cut the beam arbitrary distance x between 0 and 10 feet and apply static equilibrium conditions to the left hand section as shown in figure. We can do this since as the entire beam is in static equilibrium, then a section of the beam must also be in equilibrium. Here is the left section of the beam x feet long, where x is an arbitrary distance greater than 0 feet and less than 10 feet. Notice, if we just include the 5,000 pound external support force, the section of the beam is clearly not in equilibrium. Neither the sum of forces, translation equilibrium, nor the sum of torque, rotational equilibrium, will sum to 0 as required for equilibrium. Therefore, since we know the beam section is in equilibrium, there must be some forces and a torque not accounted for. In figure 2b, we have shown the missing force and torque when we cut the beam. The internal shear force and bending moment at that point then become an external force and moment acting on the section. These are shown in figure 2b and labeled V means shear force and M means bending moment. Sum of forces in y direction is 5,000 minus 10,000 minus V is equals to 0. Solving for V2 is equals to 5,000 and sum of the torque about the left hand, and we will get here the value minus 10,000 into minus plus m equals to 0. Next, substitute the value of V from the force equation into the torque equation, solving for M2. A useful way to visualize this information is to make shear force and bending moment diagrams, which are really the graph of the shear force and bending moment expressions over the length of the beam. Shear force and bending moment diagrams, here axial load diagrams. Here you are seeing a bar of length. There are three portions L, A to B, B to C, and C to D, and there are some forces like 5 kilonewton in the left direction and 8 kilonewton in right direction, 4 kilonewton in right direction, 7 kilonewton come in the left directions. We will draw the free body diagrams and will analyze these force and draw the torque diagram. These are a quite useful way to visualizing how the shear force and bending moment vary throughout the beam. We have completed our first shear force bending moment problems. We have determined the expression for the shear force and bending moment in the beam and have made accompanying shear force and bending moment diagram. Of special importance are the maximum and minimum values of these quantities. The shear force and the bending moment diagram are useful ways of understanding how the shear force and bending moments vary throughout the length of the beam. To provide a clear understanding of these diagrams, a detailed explanation of how to construct and interrupt is given. Here a concentrated load and a simply supported beam. If we start with a simple beam with a concentrated load, find reactions, cut through beam to the left of the end load P. Free body diagram. Equilibrium yields V and M for the left side of the beam. Cut through the beam to the right of the P. FBD equilibrium yields V and M for the right side of the beam. In figure you can see. The shear force diagram, the shear force at the end is equal to the reaction, remains constant until the point of load P. Shear force decreases abruptly by an amount equal to P. In the right hand part, the shear force is constant but equal to the reaction B. The equations for movement are plotted below. The shear diagram of the beam, the bending moment diagram. The bending moment in the left side increases linearly from 0 to the support to P at the concentrated load x equal to A. In the right side, the bending moment is again a linear function of x varying from P at x equals to A to 0 at the support x equal to L. The maximum bending moment is therefore PAB by L, which occurs at the concentrated load. Next, look at a simple beam with a uniform distributed load of constant intensity W. Find reaction because the beam and its loading is symmetric. The reactions are equal to WL by 2. The slope of the shear diagram at each point equals to the negative distributed load intensity at each point. dV by dx is equals to minus Wx. Therefore, the shear force and bending moment at a distance x from the left end are dV by dx is equals to minus Wx, dm by dx is equals to V. These equations are valid through the length of the beam and can be plotted as shear and bending moment diagrams. The maximum value occurs at the midpoint where dm by dx is equals to V equals to 0. Maximum bending moment will be equal to WL square by 8. The slope of the moment diagram at each point equals to the shear at each point. This is the procedure. First, draw the free body diagram of the beam with sufficient room under it for the shear and moment diagrams. If needed, solve for support reaction first. Generally, we needed this. Draw the shear diagram under the free body diagram. The change in shear equal the negative area under the distributed loading. Label all the loads on the shear diagram. Del V is equals to negative integration of Wx dx. Draw the moment diagram below the shear diagram. The shear load is the slope of the moment and point moment result in jump in the moment diagram. The area under the shear diagram equals the change in moment over the segment considered up to any jumps due to point moments. Del M is equals to integration of Vx dx. Label the value of the moment at all important points on the moment diagram. These are the common shear force and bending moment diagram of the common structures. First the point load at the center, then a couple, uniformly distributed load, uniformly varying load, and we can see the diagrams of shear force and bending moments. Thank you.